everyone. My name is Mengke Zhuang. I'm a research associate from University of Bristol. Today I'm going to present our work on reliability analysis for shallow shell structure on estimating small failure probabilities. Right. Look back into the history. The de Havilland disaster is probably the most iconic accident that leads to our modern consideration of crack propagations. The fundamental cause of this accident is basically crack initiating from a rivet hole and propagate through the pressurized cycles. That means that we need failure analysis and a robust fatigue testing before certifications. So now if we're looking at the fatigue testing here, even if we're starting with the same initial crack size, we may end up having a different failure fatigue line. This is due to we have variations in material properties, geometry, and even loading conditions. So nowadays, reliability analysis or probabilistic analysis are often demanded so that we're taking into account of the scattering nature of the parameters. If we have, for example, if we have a two-dimensional problem that is spanned by two parameters, and each of them having a certain variation associated, and some of the combination will rise in a safe region, and some of them will fail. So in reliability analysis, we want to distinguish what is the boundary between a failure and safe. So in mathematic way, this is defined by structure load carrying capacity of structure minus the demand that is from the external load, and this is called the limit state functions. We can simply estimate the probability of failure by integrating this joint probability density function on the failure domain, or we can simply count how many samples will fail if we do iteratively compute the limit state function. So long story short, this is a whole process of reliability analysis. We start with prior knowledge on the uncertainties associated with our design parameters. We sample all the possible values and plug into our computational models, repeatedly run, and we may end up having these pretty looking boundaries between the fail and safe regions. So what is the difficulties here? Obviously, we cannot do this multiple times, especially we have FE models and probably a very complicated geometries. Especially if we're looking at very small failure probabilities. For example, military aircraft will require 10 to the minus 6 for failure probabilities. That means we need 100 million FE simulations, which is impractical to do. Improve upon the Monte Carlo simulations. In 70s, people start to use first and second order reliability analysis. This is basically transfer the entire problem into a kind of optimization strategies. So these are relatively quick to compute. But if we have a highly nonlinear problem, it's not going to give us accurate estimations. So now in the 80s and 90s, many variance reduction methods were developed, important sampling and subset samplings. They are still quite popular in use. So we now decrease the need of running a FE to like thousands or 10,000 rounds, which is a big improvement compared to Monte Carlo, but still not very ideal. So that's to say, to address the real industrial application, we basically don't have many choice but to use surrogate models. And this leads to our main goal of the work, to use multi-modality surrogate model with active learning variance structure method to efficiently estimate small failure probabilities. In general, surrogate model is an approximation of the original computational models, but built upon only limited rounds of original model. By doing this, we can decrease the computational cost from probably hours to minutes to milliseconds. And in reliability analysis, the one that is probably most used is a cleaning model. Basically forms by two parts. So the first part is a linear combination of all input parameters, and second part is standard Gaussian distributions. So that means at each point, we are not only getting a prediction of the value, we are also getting uncertainty associated with that prediction. For example, if you look at these 1D cases, at the beginning we start with very few points, and the prediction uncertainties I plot is in this purple quickly vanished bubble shape. So the nice thing about this prediction uncertainty is that we can place our next point at the place where we have the highest uncertainties, so that we put the sample point where it's necessary, and quickly we can see fitting the original model very good. Sometimes we may face a problem of even generating such training point is very expensive. For example, we have a very fine mesh FE model, or we need the experimental data to support the approximations. And multimodality model solve this by combining many cheap but low accuracy data points with only a few high accuracy but expensive to run data points. And particularly, we use co-printing model here, and again, it's forming by two parts. So the first bit is constructing a printing model for the low fidelity data, plus a discrepancy model which implements the difference between a high and low fidelity data. We look into the same example as we previously seen in last slide. Same example, but now we put many samples for the low fidelity equations, but we only need 8 high fidelity data, and you can see the root mean square error is relatively the same, 0.1 something. And this is reducing the need for high fidelity data. Now, once we construct our surrogate model, we can now think about which reliability method we are going to use. Of course, now if we have the surrogate model, running Monte Carlo is not a very difficult issue, very difficult task. So if you look at the figure, the gray points are my Monte Carlo samples. So what's the problem? If you can notice the probably only 100 samples are going to fail out of probably a million. And then if we look at even smaller failure probability, probably we're only going to have one failed sample out of 1 million Monte Carlo candidates. So that's the problem. How can we sample it more efficiently, more smarter? So if we introduce this important sampling method here, basically we need to put important sample density around the limit state functions. And usually we choose Gaussian distributions and identify the center of this important sampling. They are both the reliability analysis, or we can use the adaptive update scheme, but those are quite established methods, so it's easy to implement it. Now to unify the whole concept, we can end up having this active learning scheme. So we starting with few training points, going to end up having a not very good surrogate model. But now we can use our learning function to decide where the next point is. It's going to be either close to the limit state functions or improve our surrogate model estimations. And there are two fundamental words in this active learning field, so IGRA and AK Monte Carlo. So here is the illustration of the concept of AK Monte Carlo. Basically, we start with some initial samples in the middle field, and then you can see the red point are my new samples. They are all around the limit state functions. Then quickly approximate the true limit state. And the general framework, we can divide that into 4 modules. Basically, there are different methods in different categories, and we are free to choose and combine different methods and to do estimations. So if we look at the literature, all of these active learning methods are built upon single fidelities. Now, if you want to take advantage of multi-fidelity model, we need to figure out new active learning functions that tell us when and where to select high or low fidelity data. So this is the global arrow active learning function we use here. Basically, it's divided into 4 parts. So the new point will either give us highest contribution to the variance reduction close to the limit state, or gives the improvement for the co-meaning model. And we also introduce this distant penalty function, because we don't want all the points close together. Finally, there's the normalization factors. Regarding to fidelity selection, we have this cost-aware criteria. Basically, this equation saying is we are only going to add high fidelity data when the cost ratio, when the error ratio is not higher than the cost ratio. And once we observe a convergence in probability of failure, we can stop the algorithm. Right. Now, before we apply the method to real applications, we use this 2D highly nonlinear example to validate our method. Here we introduce low fidelity equations, and we assume a cost ratio between the two equations is 10. So they are both analytical. We also try to vary the parameter C in the equations so that we can look into different order of magnitude in the probability of failure. So similar to the illustration previously for the AK Monte Carlo, but this time we notice that there are samples around the low fidelity equations, plus some samples from high fidelity equations, and they still be able to achieve good accuracy. So compared to the normal Monte Carlo simulation, we observe around 1% error. That means the method is good. And so we can proceed for the real applications. So we look into this 0.7 dreamline fuselage window, and we assume that the crack is initiated from the corner window frame. And we did the FE to kind of give an overview of where the initiation location with the direction of the crack propagations. And these are the prior knowledge on the variation associated with the design parameters. Our limit state function is written in terms of stress intensity factors. Once we exceed the threshold toughness, then we will have failure. We also try to vary the crack length between 30 to 40 millimeters, again, to look at different levels of probability of failure. And it's worth noting that the stress intensity factor will compute using the dual boundary elements method. And you can probably infer from the name, only needs the boundary to be matched. So every need all geometry to be matched, but boundary element is only around the boundaries. So this is a setup of our low fidelity model and high fidelity model. Basically, we bring comes from two different quality of mesh. So the low fidelity level requires like 24 seconds to run, and the high fidelity model needs around 2 minutes to run. And then this gives us a cost ratio of around 4. We also took our traditional way to do a pre-trained surrogate model and then plug into a Monte Carlo simulation. This is just to give a reference failure probability and assess the accuracy of our method. So you can see that varying the crack from 30 to 40, the maximum error we found is 5.4%. This for a small failure probability is still a bit challenging, but it's in a good level of accuracy. But in terms of the number of needs for the high fidelity equations, here is almost around 40 compared to the original traditional way of pre-trained cleaning model needs 267 to achieve a good level of accuracy. This is a significant reduction in the computational cost. Yeah, to sum it up, we use this active learning function with multi-fidelity model to estimate small failure probabilities, and we use a 2D example first to validate the method. And we apply the method for the fuselage window structures. We can observe that this has a significant reduction in terms of the number of runs for the high fidelity model, but still we have good accuracy. And the limitation is quite clear. If we have a better surrogate model for estimation, we will have a better estimation of failure probabilities. And now we are trying to apply the same method for multi-failure mode. That means we'll have more limit state functions and probably time variant probabilities. And I would acknowledge that this work is funded by ATI supported advanced timing project collaboration with Sound Systems. And thank you. Happy to take questions.